Welcome back to section 6.2, where we're talking about angle and orthogonality in inner product spaces. So at the end of last video, we were finding the norm of some vectors, and we found somebody that was orthogonal to our vectors in P2. So let's go ahead and use our inner product to find the length squared of f. So that will be 0 squared plus 1 squared plus 0 squared, which will be 1. And for g, it'll be 1 squared plus 0 squared plus 1 squared, which is 2. Okay, and the square roots will be undone by the squared here. And if I do f plus g, let's just quickly remember what that would be. So that would give us 1x squared plus 1x plus 1. And if we do the magnitude of that, it'll be 1 squared plus 1 squared plus 1. Oh, when we square it, will be 3. And hopefully you notice that 1 plus 2 equals 3. So I want you to take just a second and now go over here to the matrices example. We came up with, well, we had our U matrix, and then we had you come up with a W matrix that was orthogonal to that guy. And I came up with this one. You probably came up with somebody else. But I want you to take just a second, find the magnitude of U squared, the magnitude of W squared, and the magnitude of U plus W squared. And we'll pause for that. All right, so we're back. On mine, well, our magnitude of the U vector squared would be 30. We actually did that work previously, so if we just square this, we get 30. Your W vector, which you just made up, is going to be different. I got 5 for mine. Yours may be different. But when we add those together and then find the magnitude squared and get 35, hopefully you're noticing that 30 plus 5 equals 35. Now, here's the important question. Why is that? What's going on here? Well, let me just quickly remind ourselves that we've got the magnitude of f squared plus the magnitude of g squared equals the magnitude of f plus g. I'm going to do just a big old vector squared. And hopefully you recognize this as somebody you've seen a lot before. A squared plus b squared equals c squared. And so that is just the Pythagorean theorem. And notice that the Pythagorean theorem works on right triangles and only right triangles. So if they have a 90-degree angle, but we forced that, or well, we noticed that because f and g were orthogonal, and we actually forced you to pick a w vector that was orthogonal to the u vector. So you'll notice that happen over here. So again, magnitude of u squared plus magnitude of w squared equals magnitude of u plus w squared, again reminding us of the a squared plus b squared equals c squared, which happens on right triangles and only right triangles. So this then is what we call the generalized Pythagorean theorem. Ooh, let me slide that over. So if u and v are orthogonal, then magnitude of u squared plus magnitude of v squared equals magnitude of u plus v squared. So we have our vectors, and since they're orthogonal, they make in their space a 90-degree angle, or pi halves radians angle, and so they in essence make a right triangle. So, and the cool thing about this is it's actually a two-way theorem. This is an if and only if. So if this is true, then the only way that can be true is if the two vectors are orthogonal. Pretty spiffy. So let's now take a look at yet another example. Okay. In our last activity, number 6, we found out that f inner product g being an integral is an inner product. And we chose let's let A be -1 and B be 1, and calculate the inner product of f with g, where f vector is f of x function, which is x, and g vector is g of x function, which is x squared plus 1. So let's do that. So our definition of our inner product here is going to be -1 to 1 of x times x squared plus 1 dx, which is -1 to 1 of x cubed plus x dx, which, if we're careful, I'll actually show you the shortcut here in just a second, but if we aren't careful, we'll just go ahead and get x to the 4th over 4 plus x squared over 2, evaluated from -1 to 1. So that would be 1/4 plus 1/2 minus 1/4 plus 1/2, but that's 0. But I expected that since x cubed plus x is an odd function, and an odd function integrated between symmetric limits is always going to be 0. Remember that from Calculus 1? So we'd have positive area here and negative area here, and they would just exactly cancel out on odd functions. Okay, so I'm going to pause here and let you find the magnitude of f, the magnitude of g, and the magnitude of f plus g, and then square each of those. And notice that they are orthogonal, so something very important should happen right here. Okay, and we're back. So I found out that the magnitude of f squared, which is f inner product f, works out to be 2/3. Magnitude of g squared is, and realizing that this is going to be an even function because it's a squared, I can do 2 times the integral from 0 to 1. And when I worked that all out, I got 56/15. And then I ran out of space, but I worked this one out to find out that f plus g magnitude squared is 22/5. And if we look at our calculator here, we see that 2/3 plus 56/15 is 4.4, which is 22/5, as it should be, because f and g are orthogonal, so the angle between them is a 90-degree angle, aka pi halves radians. Okay. All right, so how is this tying back in with stuff in chapter 5? So in chapter 5, we learned about row space, column space, and null space of a matrix. If we let our A matrix be this guy, let's find a basis for each of the row space, column space, and null space. I happen to have that A matrix in my calculator, and so let's do some matrix math on matrix A. So if we RREF matrix A, we get 1, 0, 2, 0, 1, 1, and 0, 0, 0. So that tells me that a basis for the row space would be either the first 2 original rows if there have been no row swaps, or I could, since the row operations don't change the row space, I could use these first 2 rows of the RREF matrix because they have the leading ones. So I could use either -2, 1, -3 with 0, 2, 2, or I could use 1, 0, 2 together with 0, 1, 1. They will cover the exact same plane, just in slightly different ways. Now, row operations can and do change the column space. So for the column space, we're going to need to use the vectors -2, 0, -1, and 1, 2, 3. And the null space of matrix A is what gets sent to the 0 vector. So if I augment by the 0 vector here, I'll find out that I'll need a parameter. X3 is t, then x2 would be -t, and x1 would be -2t. So the null space would be the vector -2, -1, 1. And we'll need to find the null space for A transpose, so that'll take me just a second. Let's pause right here. Okay. So if I RREF matrix A transpose, I get the following: 1, 0, 1/2, 0, 1, 5/4, 0, 0, 0, which if I then augment by the 0 vector to find the null space, and I let x sub 3 be, how about 4t, then x sub 2 will be negative 5t, and x sub 1 will be negative a half of 4t, so that would be negative 2t. So the null space of A transpose is going to be negative 2, negative 5, and 4. So we'll stop the video right here and pick up on the next one.